Today we are going to discuss a very interesting topic of linear mean square error estimation. All right, so this is the last slides that we had last week. We are working with system identification. System identification is that I have a system input X, observe the system output Y. Then we want to find the system itself, H. In other words, we have some of the training input. So the X is known. So in this case, it's a identification, right? Identification. So I know X, I know Y. I want to find the system H. I want to find the system H. So we can think that as we have some of the pilot signal X, we already know. I have some result Y, and I will have something that I expected, some X hat or something that I expected because I know the input. And then I get actual output, which is Y, or Y hat versus Y. Then I want to find out what this H is, system identification. We mentioned at the very last page of last lecture saying that we would like to do with the second order statistics. We would like to use the cross correlation, autocorrelation to find H. Instead of doing H equal to Y omega over X omega in the frequency domain, we'd like to use that. We'd like to use that as a cross correlation of output Y and input X over the autocorrelation. If you look at that, this is the autocorrelation of the input signal. And using the second order statistics, we can have a better result for the system H. There are a few reasons for that. The input signal, output signal, those are the sequence, right? So those are not fixed samples. We may have a lot. So I'm only going to take a portion of those samples to find H. And then I hope this H can work for all future input X. Another reason we can argue that is that the input signal, output signal, they're all random. They're all random. It's difficult for me to find capital Y, capital X. It's a random signal. For example, I need to have an estimator. I need to have a communication system. Any of those things that the signal coming in that change all the time. I want to use only a portion of the observation of these random variables to identify the system. And then if I know some statistics about this random variable, and then I can say, this system define the system or identify the system that can work for this kind of random signals. All right, so that's what we really like to do with this second order statistics. We're using the autocorrelation, using the cross correlation of input and output. Today we are going to look at that from another angle. It's coming from the error criteria. What do we really want to do? What's our final goal in order to find we call it optimal system? We call it optimal H. We want to find. We're going to look at a concept called optimal linear filter. Optimal in what way, or optimal in respect to that I can minimize the error. So first we need to define error criterion. And then with that, we want to minimize that error and give me an optimal filter. And we call that a linear mean square error estimator or linear mean square error filter. And with that, we have four different sections in that. The first one is error performance surface, how to see the error performance surface. The second is derivation of linear mean square error estimator. And third, we want to explain that using a principal component analysis. And then the fourth, we bring out orthogonality principles for optimal linear filter. So let's look at those one by one. All right, so the error criteria. Now we know that we have a signal X coming in, let's call it Xn, and then go through my system, we derive yn. Right. So for simplicity, let's look at just a delayed tap. So what we have here is I have a x coming in, x in. Delay tap is we delayed by c to the power -1. So here is xn minus 1. And then this x is using, we have a filter, right? Filter h1 coming here. Well, let me draw this way, according to what we had before. Tap delayed line. So it comes here multiplied by a weight, which is, let me call it h1. Here is multiplied by another weight called h2. Then all these will adding together. And then we have some other delays here. That this is the last one. Let me call it hm. All right, and adding this. Then we have just one output, we call it y. So this is the tapped delayed line. And we have a delayed element. So each delayed element will multiply by weight h1, h2 to hm. And then we have output y. What is that? Now this is a FIR filter, right? Finite impulse response. I only have feed forward. I don't have feedback loop, only feed forward. And then the input is a sequence xn. I actually using the sample-wise xn, xn minus 1, xn minus 2, all the way to xn minus m. We take that m plus 1, m, input data, produce one output using an FIR filter, where here the coefficient of this FIR filter, they are the weights on each delay tap. Okay, so for this simplified, this is FIR filter. The output for the input with a length of x1 all the way to xn. Take that as a vector, and the output is only one value. It's one scalar. It's y. To find the error, now suppose I have a desired y. Let me call this estimated y with a hat. Usually that's the estimation. And I have a ground truth y. I know what it should be y. And then the error, of course, is between these two. Right? This is the error between the estimation and the ground truth. So for the error criteria, what we can do is we're looking at this error. We know for the error itself, I want it to be 0. Whether it's positive or negative, it's not good. So there are error criteria. I can take the absolute value of error. I can use absolute value square, which is E times E conjugate, if my signal is a complex signal. Right? And we can have higher order as well. So usually we are using those two, either the absolute value of E or using absolute value of E squared. This is called the squared error or square error. So if I'm going through many groups of those inputs, get many of those y's, and what I can do is I can do an average. Average this, average this. When I do the average, we are taking the mean. So it's a mean square error. Mean square error. This is the error criteria. I can use both, and usually people will pick up this mean square error. The reason for that is it gives us a very nice, in the optimization, it gives us a very nice function. So I can minimize the mean square error. In optimization, it gives me a very nice, smooth, bowl-shaped curve that I can do something, for example, the gradient, to find a minimum point. So here, first we kind of fix our error criterion, and we are using the mean square error as our error criterion. What we want to do is I want to minimize this. Let me write this again. Expected value of E square Okay, this is our error criterion. Take average or take mean, that's the same thing, expected value. And this is the error I want to minimize. Okay, now since we are talking about the complex value, let me using a complex number. Let's say I'm changing this H to C, just to say I have a complex filter as well. Those numbers, they are not real, they're not just real, they are complex. I'm using a C1, C2, all the way to Cm. When I do this, I put a conjugate here. It doesn't matter, right? It's complex number. I put a conjugate here. I want to make it the x times c conjugate. When we discuss about complex, in the complex region, and the multiplication is I like to use a x times another conjugate, just like that, e times e conjugate, and using that as the product. So we have here now y, the estimated y is equal to x here, this is the 1, xn times c1 conjugate plus xn minus 1 c2 conjugate all the way to xn minus capital M times cm conjugate. So that's the FIR filter we have. We have the coefficients, which are complex number c's. Okay, and let me simplify that as well. The input signal x is random variables. So I take off this time index n. I just think the input is we have here, let me call this x1, call this x2, and call this xm, because they are random numbers. They are just random variables. And it can have many different realizations or implementations when you plug in the real samples. So I simplify that. Instead of a time series, I'm just saying, well, I have random inputs. Those are the random numbers. x1, x2 to xm, cm. All right, so here I have the estimation. Here I have the estimation. Now, first let's look at the error surface, the error performance surface. Error performance surface, this is the error. This is error performance. If we're talking about error performance surface, I'm trying to draw something with, let's say, if just one dimension. Let's say one dimension. This is my error, mean squared error, and putting here. What is the x-axis? Well, of course, that's my variable, right? In my case, that's c. C. I'm trying to find c to get the minimum error. So c is some variables I can choose. Now this is c is just one dimension. So let's say I have just one variable. So c I want to adjust, and then to see what kind of what c will you choose that will minimize this surface, which is the error surface. Now, if I have two parameters, C1 and C2, so this error surface is, in this case, hopefully, it's a bow shape like this. So let me draw this 3D as bow shape. So again, this part is my error surface. In my case, is the mean square error. I want to minimize that. If the function looks, the surface looks like a bow shape, I know this is the minimum point. So I can find out this point here and here. So this is C1, C2. Let me call it 0, 0. Just stands for the best point. Once you find the C1, C2 at the 0, that's the best point. That's the best parameters you can find in terms of minimizing the error. All right, so with C1 to Cm, if you can picture, we are working on n-dimensional space. C1, C2, C3, all the way to Cm, and you pick up those variables. You want to make sure that this error surface is minimized. Okay, so this is this is the error surface. Mathematically, what we define is I'm defining the error surface P as a function of parameter C. Now, I'm using 1C, just a shorthand. This is actually a vector. C, this vector C is C1, C2, all the way to Cm. Right. So it's a function of those m variables. In my case, this error surface is the mean square error. Is the mean square error. Right. So the mean square error, if I write this out, E, what is E? E is y subtract y hat times y subtract y hat conjugate. Now let me write out one more step here. Y hat, due to our design, y hat is this. It's linear filtering. That is my input vector x times the vector of my filter. So in a shorthand, I can write this as what is this? This is a C conjugate, C Hermitian times x, where C is this vector. And x is another vector, which is the input signal, x1, x2 to xm. Right? So what we do here, H stands for Hermitian transpose. So C, let me just write out one more thing here. C Hermitian is equal to the transpose conjugate. So we are C1, C2. First you do transpose, and then the conjugate. It's conjugate transpose. So it is that. X is this vector. So you multiply these two vectors. It's one is a row vector times a column vector. Then you have only one value. One value is y hat exactly in this expression. Okay. So we know that in short, I can write this as C Hermitian times x. Right. Everything now here, everything is this is a vector form because everything is complex valued. So I'm using C Hermitian instead of C transpose. Right. It's the same. Okay, so I have this. This is my E. Therefore, I have another E conjugate is y subtract C Hermitian x conjugate equal to this. So this, what is this part? This part is y conjugate subtract C Hermitian x conjugate. That is equal to x conjugate C. So here I have a x Hermitian times C. Okay, in this. All right, in this. Then expectation, I keep it. Then these two terms, let me spread this out. So I have y times y conjugate subtract C Hermitian x times y conjugate subtract y times x Hermitian C, and then plus the last one is C Hermitian x Hermitian C. Okay, so I have those four parts. E of this, E of this. E is expectation, so I can take this. It's a linear operation, so I can take that into each inside terms. So work on that. Okay, so the first term is expectation of the output signal y. This is y absolute value squared. Now, since we know the output signal is it's a one scalar. So we have here is a y absolute value squared. This is just a dimension of 1, and we call that the expectation of y. We call that P of y. P of y has nothing to do with my coefficient C. So it's independent of C here. The second term here is this. Now expectation of this in this bracket. C, I can take this out of the expectation because C is the deterministic parameters I want to find. The random part is my random signal, random X, and of course, output signal Y is also random. So the expectation is taken at X and the Y conjugate. Okay. X is a random signal, Y is random signal. So I put in expectation here. And then the last part, the third part is expectation of Y, X summation here, times C. C again, I'm taking this out of my expectation. C is deterministic, taking out the expectation. And I don't want to mess with the order because in matrix form, left multiplication, the right multiplication is different. So I keep it at the right side of this. The last part, I can take the left multiplication of C Hermitian here, expectation of X Hermitian, and then right multiply by C. Okay. Now I have those 4 parts. Let me define the autocorrelation X Hermitian. Let me define this as R. What is the dimension of R? X is a vector. So that is dimension m times 1. X Hermitian is a row vector, x1 conjugate, x2 conjugate to xm conjugate. This is a vector, row vector dimension of 1 times R. Therefore, here, R has a dimension m times m, and R is the autocorrelation matrix, of the signal. So we can write this out. If I want to spread this out, this is expectation of x1 conjugate, x1, x2 conjugate, and here is x2, x1 conjugate, x2, x2 conjugate, all the way to xm, x1 conjugate, x1, xm conjugate, and then the last one is xm conjugate. Expectation of this. Okay, that is the autocorrelation matrix. Now we have something. Remember the first slides we are showing that I want to take the autocorrelation of the input signal. I also want to take the cross correlation. So we got this here too. And this is the autocorrelation matrix. Autocorrelation matrix has a very nice property. If you look at autocorrelation matrix, this autocorrelation matrix is symmetry. It is conjugate symmetry. So we take the Hermitian matrix that is equal to R. So you take the transpose and then conjugate. It's exactly equal to itself. So we call that a symmetry, but in a sense, it is Hermitian symmetry in a complex sense. We also define here E, X, and Y conjugate expectation. We call that D, which is the cross correlation between the input and output. Now, input is a vector, X is a vector. Output in this case is only one value. It's a scalar, Y. And using the same thing, and X is a random vector, Y is a random variable. It's complex, so X times Y conjugate expectation. That is the cross correlation D. What is the dimension of cross correlation D here? There will be a vector, m times 1. Right? It will be a vector because X is the vector, m times 1. Y is a scalar, 1 times 1. So therefore, this value D is m times 1. And that is the cross correlation. Now, suddenly we have both. We have the autocorrelation and the cross correlation. That exactly when we're dealing with a large data set, and we are dealing with the random signals here. Okay, with that definition, let me go ahead with this equation. This is equal to, the first part, let me call it P of Y. P of Y is independent of C, right? And then I have C conjugate times D, subtract D Hermitian times C, plus C Hermitian R C. Okay. So this is what we have for my error surface. Remember, this entire thing we are calculating PC is the error surface. So this is PC as a function of C is also equal to expectation of absolute value squared. The error surface is the mean square error. So with that, this is a function of C. What's the shape of that? I want to see if this is indeed looks like this bow shape, looks like this. And if you look at this equation here, it's indeed this surface looks like a bow shape. It's a function of C. These two terms, it's a linear function. Linear function, it doesn't matter, it's just a linear line. It can be any direction, but it's a linear line. Now this part is a quadrature term. This quadrature term will give us a shape that is curvature shape. It's a very nice shape equation here, C Hermitian R C. Okay, in a matrix form, this is a nice second order term. Because I have very good property of this R. R is autocorrelation matrix. We already said this is autocorrelation matrix. Autocorrelation matrix is symmetry, and then in this case, autocorrelation matrix has also a very nice property. It is a positive definite matrix. R is positive definite matrix. From linear algebra, we know a positive definite matrix, meaning that if you have any x for any x, for all x, this will be greater than zero. For all vector x, you multiply by that. Of course, you need to make sure that the dimensions are fit. And then this product will always be positive. And then this matrix is called a positive definite matrix. And we can also have the called a positive semi-definite matrix, which is that I have this greater than or equal to 0 for all x. This is called the positive semi-definite matrix. But for the correlation matrix, in practice, that is always a positive definite matrix. Okay, so let's just remove this part. For a positive definite matrix, and then I will have for this term, I will have a bow-shaped term. And that is the picture I just drew right here. Let me save time to. So if I have only two dimensions on C, C1 and C2, so this surface is this surface. It's a convex surface. It's a convex surface. Okay. For high dimension, in this general case, C is m-dimensional vector. We also have in the high dimensional space, we have this convex bow. And then we will have a minimum point corresponding to the minimum position here. Okay. What is the minimum point that we can have? First of all, you can think that if you think this as just one value, maybe you can think of this as R times C squared. If you think that as is one value for scalar case, not in matrix form, vector form, when I is greater than 0, and then you have this shape. If I is less than 0, you have this shape, so you will not be able to talk about a minimum point in this case. Okay, so okay. Here we are talking about the matrix form, so therefore this here, this is R. Now in this case, for any x, positive definite matrix is that for any x, it is not equal to 0. I left it here. It's not equal to 0. Then I have this form. Of course, if you give me a 0 vector where x with all the elements are zeros, 0 vector, then of course this entire thing will become 0, which means that if x equal to 0, sure, we have this equal to 0, right? The same thing as when we're talking about this RC square. When C square is equal to 0, even if R is positive number, if C is equal to 0, that's 0. So since we know this and also that, now what is the minimum value I can get for this guy? Well, the minimum value is 0. It's only when X is equal to 0. So I get a minimum value. So using that part, somehow I can find this minimum value of C. Of course, in this case, it's a little complicated because I not only have this term, I only have those two linear terms, one here, one here. So you can think this term is a very nice convex function, and you can find the C and make a minimum point. But those two terms are the linear terms. So you subtract those two linear terms, and that's not the best C you can get. So if I can change that, let's say, if I can somehow change that into a format plus C time, instead of R, change that to R cubed. If I can change it to this, combine these two linear terms, then I can say something. When C is equal to 0, I get a minimum value for my error surface. So this is the direction I want to do. So how can we do that? To construct that, the error surface, now what we can do is we can put in this term here is R C subtract D commission of R-1 RC subtract D, subtract D -1 D. Okay, let me construct this first, and let's find out, is this really the error surface that we wrote before? So what is this? This is, so we have to find this. So RC Hermitian, there will be C Hermitian, Hermitian, subtract D Hermitian times R -1, RC subtract D. Okay, let's look at this part in the middle. Now we know for this, remember we have a very nice property for my autocorrelation matrix, which is right here in this box. Is R Hermitian is equal to R. It's a symmetric matrix, autocorrelation matrix. So we remember that. So R, just let me write out here, R Hermitian is equal to R. Okay. So we write out here Py plus, spread this out, C Hermitian R Hermitian R -1 R C, just subtract D, multiply by that, subtract D Hermitian R -1 R C subtract D, and then subtract D R -1 D. Py plus the first term is in here is R Hermitian R -1 R C. Then second is subtract C Hermitian R -1 times D. The third term here is D Hermitian R -1 R C. The fourth term is plus D Hermitian R -1 R, excuse me. And this was D, so let's subtract D. Then we have subtract D, Hermitian R -1 D. Okay, so write this out. Now we do some cleaning. So this term canceled out. And we have here, this and this cancel out. R inverse times R. So it's a identity matrix I. So it's canceled out. Here, very nice, because C Hermitian, R Hermitian is equal to R. We got this. So again, these two canceled out. So that's equal to R times R inverse. That is my identity matrix I. So canceled out is I. And this is I. So what we have here, after this house cleaning, we find out this is PY plus C Hermitian R, which R Hermitian, again, I don't need to have a Hermitian here. It just simply as R is the same as R times C, subtract C Hermitian D, subtract D Hermitian C. Okay, so very nice. We actually recover this original line right here. It's, sorry for this, messed up. It's actually moving this part here. So it is a line here. It is a line here. Somehow I messed up with this writing, but we can see, indeed, we kind of combine these two linear terms into this second order term. So we have here putting in this line right here. So let me remove these derivations. We know they are the same. So we know this is my original line. And indeed, I write this into in this format here. This is a second order, it's a quadrature form, very nice. It's only of one of the vector times R inverse and times this vector. Now this term, the third term, this term is again, is independent of C. So same as the first term, it's independent of C. So it's independent of variable. We're only looking at this part. When R is a autocorrelation matrix, R is a positive semi-definite matrix. R Hermitian is the same, and R inverse is also a positive definite matrix. Okay. Therefore, we will have this term here is R -1 times Z. Let me use an arbitrary vector Z, Hermitian times R times Z will be greater than or equal to 0 for all Z. And that is only one time this is equal to 0 is when Z is equal to 0. Z is equal to 0, this entire thing becomes 0. So in this case, the minimum value of PC can be found, minimum with respect to C, can be found is PY, this, the middle term becomes 0. That's the minimum I can get is 0. And the last term has nothing to do with C, so I copy it here. This is the minimum value I can get, where this best C, called the C naught, is equal to what? Well, it comes from here, right? It comes from here. The best position is when I have RC subtract D equals to 0. So this is the best C. When this vector here is my vector Z is 0. And then we find out RC0 equal to D. C0 is R inverse times D. Inverse times D. At that time, I find the minimum mean square error. Now remember, this is error surface. The minimum mean square error is given by PY subtract D Hermitian times R inverse D. And I can also write this as PY subtract D Hermitian times this. What is that? Well, this is my C0. That's the optimum filter parameters. Okay. So here is the derivation of that. And we have here, this is how we calculate the best coefficient, best field coefficient for my estimator of the C's. How to calculate that? Well, that's indeed, we are taking the autocorrelation matrix, taking the cross correlation. So autocorrelation matrix inverse multiplied by the cross correlation. There we will have the best coefficients. And then the minimum error is calculated when this is the output. I'm looking at output y times y conjugate. And that is the cross correlation times coefficient, subtract coefficient. That's the minimum error I can have. If we're looking at this box, the red box, what does it look like? Now, a little abuse of notation, and this is the cross correlation over the autocorrelation, right? So here is the cross correlation of x and y. And here is the autocorrelation of x and x. Okay. It's abuse of notation because we know we cannot I cannot write this for a matrix. This is a r negative 1 to the left. It's different from r negative 1 to the right. So it's just I'm using this for easy notation here. If we flick back to the previous picture, yeah, that's exactly what we have here, right? This is exactly what we have here. It's kind of very similar. We are trying to find the best system, and it is cross correlation over the autocorrelation. Cross correlation of output and input over the autocorrelation of input. So indeed, that's in general, when we're calculating the optimal linear filter or the optimal linear estimator, we find that this is the best solution. In this case, let's say if I have my error surface P of C, if C has a little deviation from the optimal value, I'll call this C tilde. So the parameters is a little off from the optimum parameters I can get. So we have a C tilde is some of those deviations. And then I have here is P C0 plus C tilde Hermitian R sub times C tilde. Okay. This is the minimum mean square error, which is this part that we can get. And this part, we call that excess error. We call that the excess mean square error. The excess mean square error. At the optimal point, when C tilde is 0, that means I landed exactly on C0, and this part becomes 0. The excess mean square error becomes 0. Because it has this quadrature form, we know I is a positive definite matrix. Therefore, this term is always non-negative. When have all other non-zero C tildes, this term, the excess mean square error, will be positive. And that's something is really excess. The excess, that's something that's additional. And I want to minimize that. I want to remove that equal to 0. All right, so remember this. This is in the red box, and we call that the normal equation. The normal equation to calculate the linear optimum filter or the linear optimal estimator in the sense of minimizing the error criteria, minimizing the error. Now the error criteria we are taking is the mean squared error. It's the mean squared error. If you're taking that, that's the optimal filter. I got a mean squared error for the output. So next time I'm trying to find out the physical meaning of doing this. And what we are going to do is we are using a so-called principal component analysis. You may have heard this a lot in any of the optimization class or even the control class. You have heard the PCA. And what we really want to do is just give me 1 minute to start this. So the principal component analysis, what are the principal component? is we need to do a eigen decomposition of my matrix R. So this becomes a Q lambda Q Hermitian. Now remember, R is a matrix. This is my autocorrelation matrix. So expectation of x1, x1 conjugate, expectation of x1, x2 conjugate, all the way to expectation of xm, xm conjugate. And you can take the expectation out of this matrix. So this is my autocorrelation matrix. Then I want to decompose into this form. Q is a very nice matrix. We call it a unitary matrix. It's let me just put in a vector Q1, Q2, all the way to Qn. Delta is a diagonal matrix, or lambda. Actually. Lambda is a diagonal matrix, so it's lambda 1, lambda 2, all the way to lambda m. All the off-diagonal components are zeros. They are all zeros. And then the last term here is Q Hermitian, so which will be Q1, Q2, all the way to Qn. So it's this. Okay. This is called the eigenvalue decomposition. We do this matrix, we spread into these three parts. Q1 conjugate is equal to 1. Q1, Q2 conjugate is equal to 0. So these they are the vectors, they are orthogonal to each other. And this is the length of the vector is 1. So it's orthonormal. And then this matrix is very nice. We decompose into a diagonal matrix. And how to use that into the PCA, we will see that next time.